So we've got a special guest for our next video, which is where we're continuing to talk about the divergence. You'll recall in the last video, and my guest is Ben, so welcome, Ben.
Thank you, Mark.
Nice to have you here. And I think Zach and Ruby might be joining us shortly, but at least Ben is here right now. But in the last video that you haven't watched yet, Ben, but I'm sure you're looking forward to watching, we talked about calculating the flux through some small differential area. And so we thought we were thinking about some vector field and thinking about how much was coming out of each side of this little square. And as we thought through that, what we found was that you could actually write that with regard to what the derivatives of the different components of that vector field were. So the way that you get that flux is by looking at how fast the x component is changing in the x direction and how fast the y component is changing in the y direction. And conceptually what that has to do with is the idea that if I've got some vector field that, say, is not changing at all, if it's not changing at all, then the amount of stuff that comes in this side is the same as the amount of stuff that goes out that side. So there's zero flux, right?
Makes sense.
If, on the other hand, it is changing, let's say it's small in the x direction here and large in the x direction over here, how much flux is there then?
There's going to be a positive flux.
Right, there's going to be a net amount of stuff coming out. Now, what if I thought about the case where I had a small x component here and a bigger x component there? Would I get flux coming out in that case?
Yeah, you'd still have greater content going out, right?
Well, I think if the vector field were only changing in the y direction, right, then I'd have a little bit coming in here and a little bit going out there, and a bigger amount coming in here and a bigger amount going out there. So in fact, in this case, if the x component were only changing in the y direction, I wouldn't get any flux. Okay. So the reason I'm getting flux here, the reason that this expression sort of makes sense is that in order to get flux, I either need the x component to change in the x direction, so I get more out this side than in this side, or the y component to change in the y direction. Okay? So that's the sort of idea, and we're going to extend that idea to a sort of new use of the del operator. So you might remember the upside down triangle, right? In the past, we've used the upside down triangle with a scalar function, right, which is the gradient. And what does that tell us, Zach? That we're joined by Zach now too. So, Zach, what does the gradient tell us about?
The direction of greatest change.
It tells us about the direction of greatest change, right? And if we write out this operator in Cartesian coordinates, right, it's the partial with respect to x plus the partial with respect to y plus the partial with respect to z, right? And it's a vector operator, so when it operates on this scalar, it generates a vector, right? So I get a vector that's the partial derivative of x of that function with respect to x in the I hat direction plus the partial of the vector with respect of the function with respect to y in the j hat direction plus the partial with respect to z in the k hat direction in Cartesian. And you can do this in other coordinate systems as well, but you need to be a little careful about how you do it in other coordinate systems. Now, we could also, come on in, Ruby's here too. Now, the operator, the sort of other way you can think about this operator, or another way you can think about this operator, is not just as something that can operate on a scalar, but also as something that can operate on a vector. So we're now going to take the del operator, and instead of operating on a scalar, we're going to operate on a vector function, on a vector field f, right? So this is some function that takes a given position and returns a vector, right? Does that make sense, Ruby?
Yes.
So can you think of an example of a vector field?
No, because I only just walked in and I was
Okay, well, so one example of a vector field could be, for example, the velocity field in a river, right? At each point in the river, the water has a different velocity. So you actually need a vector at each point in space to talk about how the water's moving. So the divergence, if we look at the definition of the operator, this sort of use of the dot here is a little bit of a sort of notational cheat to basically tell us what this means is we're going to operate on the first component of the vector with x, on the second component of the vector with the partial with respect to y. It's like a dot product. So if we write this out, I'm going to get the partial with respect to x of the x component of this vector field, right? So if I write this out, this vector field in a little more gory detail, it's got some x component that depends on where I am, plus some y component that depends on where I am, plus some z component that depends on where I am. So it's going to be the partial of the x component with respect to x, plus the partial of the y component with respect to y, plus the partial of the z component with respect to z. So this is what's called the divergence of a vector field. And what it actually tells you is something about how much flux is being generated at a given point in the vector field.
Why is that?
So let me first say a little bit about what another way of thinking about that is it sort of tells you how much of a source I have at a given location, right? So for example, if I thought about an area where I had a faucet, right, and there was water coming out of the faucet and then spreading out, right? The divergence of this vector field, I would get a divergence here where I actually had water entering the system, but I would not have a divergence here because of the fact that the amount of water that's going into this point is the same as the amount of water that's coming out of this point, right? So when I've got a divergence, what that tells me is I actually have more stuff going out of the point than coming into that point. That's what a positive divergence means. And when I have a negative divergence, it tells me I have more stuff going into the point than coming out of the point. Okay? So it's sort of a flux per unit area or a flux per unit volume if you're in 3 dimensions. Now, the reason that that is the case is that it sort of relates back to this derivation we did in the last video, which you missed, Ruby, but I'm sure you're looking forward to seeing.
Indeed.
When I've got a vector field that's changing in x, what that tells me is that the x component of the vector field maybe is smaller here and bigger here, right? The only way that that can happen is if I've actually got some more stuff coming out of this box than is going into this box, right? So that's why the divergence contains this partial of the x component with respect to x, partial with the y component with respect to y, and of course in 3 dimensions, partial of the z component with respect to z. So the sort of idea of divergence is directly connected to flux. It's sort of the local way of talking about flux. We've so far talked about flux at a sort of integral level. Divergence allows us to start to talk about flux at a differential level, and in the next video I will say something else about this that I have not thought of yet.